I have interest this morning in a claim that I made when investigating my kinematic quantities. Here, the average velocity, the change in position divided by the time in which the position changes, and the acceleration also described on average, so I suppose I'll add a bar there. The change in the velocity divided by the time in which the velocity changes. I mentioned, and everyone agrees, that there's a great utility in describing these things graphically. In fact, what I did when considering motion with constant acceleration is I made a graph, somewhat nostalgic now like this, where I made a graph of the velocity as a function of time. I suppose that I start here with some initial velocity, and in motion with constant acceleration, that graph appears, as I expect, as the graph of a line. It's linear, because I know that the slope is the acceleration, and I'm talking about motion with constant acceleration in general, and so that slope should be constant. And the trick that I was interested in is I discovered, through some very, very simple arguments that I don't need necessarily to repeat, that if I compute this area between the velocity graph and the time axis, that this area that gets computed here is in fact equal to the displacement delta x. And in this particular thing, and you can go back and review it, if I appreciate the fact that I can divide this up into a rectangle and a triangle and compute the area, I discover, as I already suspect and we've already established, that x is equal to x naught plus v0t plus 1/2 at squared, that equation of kinematics that's useful for solving problems in the case of motion with constant acceleration. I mean, that is certainly true. I've taken advantage of the simple geometry of the graph, but I have to appreciate that in the future I might consider problems where the geometry is not so simple. It's entirely possible that I could have velocity that is not linear, but is in fact something sort of arbitrarily shaped, in which case I need a technique for evaluating this same idea in that context, because I would like to calculate the displacement not only in cases of motion with constant acceleration, but in cases of motion with varying acceleration. So just for a moment, I'll consider what would I do if I had a graph of velocity as a function of time that perhaps looked like this. So here's velocity as a function of time. I'm going to draw a thing that looks rather arbitrary. Instead of being a nice straight line here, perhaps there is some initial value to the velocity, but I'm just going to do like a curve like that. So here you see, just by observing the slope, that the slope of the velocity changes. It starts out rather significant, and then the slope becomes 0 at a point along here, and that clearly means that the acceleration becomes 0 at that point. The slope becomes negative after that point, and then it becomes 0 again, and then becomes positive. It's quite complicated. And it changes continuously the entire time. Now, I can describe this situation on average in order to get approximate results. And that may do, I might be satisfied with that, but ultimately, I would very much like to find exact results. That's my goal, in order to feel as though I've made a complete physics. So what I'm going to argue here in this moment is that yes, this is quite curvy, but in fact, I could come here and I could draw a rectangle that fits under the graph, and it would have a width, delta t, and it would have a height that was equal to the velocity at that point. Well, here's my issue. At the point at the top of the rectangle here, the velocity changes. So what velocity am I talking about? Well, I could say, well, the velocity on average, or I could say the velocity maybe at the left-hand side of the rectangle or the right-hand side of the rectangle, or I could say, by that I mean the velocity at the middle of the rectangle. Those are all different velocities. The average, the left, the right, the center, they're all different. But the argument that I would make to you is that they're all approximately the same. They're all just about the same value. And so I'll say, let's take the average value on that interval, because it won't make any real difference either way, and then appreciate the fact that according to my original definition of the velocity on average, I'll find the displacement delta x, which is the area of that rectangle, is equal to the average velocity multiplied by the time interval delta t. Now I have a problem. Well, I have two problems, actually. One is that is not exactly true. It's only approximately true. And the second problem that I have is that it only works well for this rectangle. If I make the rectangle wider and say, well, now I'm going to do the whole interval like I did in the first example, the first time I did this process. If I do the whole interval, now the approximation of the velocity on average is wildly inaccurate. So inaccurate that it becomes not useful to describe it that way. And since my physics is a description of the universe, I have to be more precise. Now, I know that you're already out there thinking, well, I've got an idea for you, an idea that we've already used, and that is to make the interval delta t quite small, because the smaller I make it, the more accurate the displacement on that interval, because if I reduce the amount of time, the velocity changes less. Well, that still doesn't solve what I should do in the case where I want to know what is the displacement from here to here, because the velocity changes significantly on the entire interval. Well, the solution, not a great one, but the solution, is to divide this interval up into a sequence of rectangles and consider the average velocity or the midpoint velocity or the left or the right or whatever you like at each end of the interval. And then to find the total displacement delta x. I'm going to use some math notation here. And math notation is just that. It's a way of speaking about the nature of mathematical things in a shorthand, well agreed upon style. But in this case, I feel like the notation itself has lovely meaning that we want to really internalize. I can find the total displacement delta x by adding up. And so I'll use a capital sigma. By adding up, capital sigma means the sum, to add, of whatever velocity I choose to use, whether it's average, left, right, whatever, vi, where I is an index, the first one, the second one, the third one, the fourth one. That is v1, v2, v3, v4, v5, however many v's you decide to make it up, multiplied by delta t. And I'll do myself a huge favor by deciding to use the same delta t for each rectangle. So I've improved the situation by not using just one velocity to describe the entire interval, but many velocities and therefore many rectangles, making the argument that the uncertainty, the error in each individual rectangle is acceptable. And then I add up all of the rectangles. I use the symbol sigma to represent the summing of a countable number of things. I use sigma to represent the adding up of a countable number of things. Well, I want to take this idea and make it exact. I want to take this idea and make it exact, and the way that we do that is right in front of us. I'm going to try to duplicate the graph here to the best of my ability. Sort of the same graph, like this. Very much the same looking graph. I want to make this an exact formulation. And so what I'll do, and you already know, I think the audience is probably well ahead of me on this, but it's important that we have the discussion. What I'll do is divide this thing up to, if I'm capable of it, a difficult diagram to make. I'm going to divide it up into rectangles that are so extraordinarily thin, so preposterously small, so narrow, that at the top of the rectangle, when I consider the velocity of the rectangle, the velocity does not change at all. Well, it's got to change some amount. Well, what I'm suggesting is that down here, instead of using a time interval delta t, I'll use a time interval dt, an infinitesimally small time interval. A time interval so small that the idea of a velocity on average at the top of the rectangle becomes an idea of an exact velocity. In which case, I get a change in displacement, I get a change in position, the displacement, that's the area of this infinitesimally thin rectangle that is an infinitesimally small displacement, dx, at an exact velocity, not the velocity on average, not the velocity on the left, not the velocity on the right, not the velocity at the center, but the velocity at that point multiplied by the infinitesimal time, dt. Those two things, those two statements are exactly equal to each other. Well, now I've caused a real problem for myself. While I appreciate the fact that making the interval very, very, very small makes the result exact, I do not in this moment have an idea about how you add up an uncountable number of things. I have a friend who is on the opposite end of the, I don't know, are the humanities? I guess in a sense they're the opposite end of the intellectual spectrum. An English teacher who becomes enraged in supermarkets when the when the express checkout lane says 10 items or less. It should say 10 items or fewer, because the word fewer refers to a countable number of things. Less describes a reduction of a continuum. That is, the temperature could be less. The number of people playing outside is fewer because the temperature is less. A continuum compared to a countable number. So here with these rectangles, I had a countable number, but now I've got an uncountable number. And so what I do is say that I could find the total displacement delta x. Say, once again, from some initial over here to some final over here. I can find the total displacement delta x by adding up through a continuous sum. So I use the summa, this very exotic, stretched out S-looking symbol. The velocity at any instant dt. So I perform that continuous sum, not the discrete sum. Well, I need a technique for doing that. Here's my problem now. So what I have to do, realizing that I have to add up this infinite number, I stop and I go and I take a course in calculus to investigate the techniques that have been devised, initially by Isaac Newton and Gottfried Wilhelm Leibniz, and then expanded on through the centuries to bedevil the days of young students everywhere. I study all of those techniques and I come back again to say, now, if I know the velocity at every instant in time, that is, if I know the velocity as a function of time, I tell you a time, you tell me a velocity, we know the velocity at every instant in time, I can compute the displacement. So a little bit about that technique, because I've already encountered this in one aspect of my physics, in that I've described the derivative. Now over here, by way of summary, I wrote this derivative rule that I've already made use of, and here it is as it appears on our equation sheet. The derivative of x to the n is equal to n times the x to the n minus 1. The mathy sort of longhand way of saying, in order to find the rate of change of a function with respect to the variable, you multiply by, I should be more specific on that. In the case of a monomial, something raised to a power, in order to find that rate of change, you multiply by the power and then demote the power. You multiply by the exponent and then demote the exponent. And we come to do that automatically, so that if I say the function is 3x squared, you immediately say 6x. Because the square comes down and multiplies the 3, becomes a 6. The square gets demoted to the first power, so 3x squared becomes 6x. Differentiation. Differentiation, a process by which, for example, if I have the velocity, or I have the position as a function of time, then the derivative of the position with respect to time, of course, is the velocity. Similarly, the acceleration is the derivative of the velocity with respect to time, and successive derivatives that we suggested. If I know the displacement, I find the velocity. I said that wrong. I said that imprecise, so I'm going to say again. If I know the position is a function of time, I find the velocity. Now I want to go the opposite way. Knowing the velocity is a function of time, I want to find the displacement. The reason why I paused for myself there, and it's funny because there are some issues of precision in how you talk about these things that aren't super practical when you're solving problems, when you're a student who has to perform well on a quiz or on a test, but they're really important for like the true meaning. If I have the position as a function of time, the derivative gets me the velocity as a function of time. What I want is the reverse process, sort of, where, you know what, I'm gonna write it in symbols here to see if I can express myself. If I have the position as a function of time, that's weird. If I have the position, if I have x as a function of x, that's gonna fester. If I have the position as a function of time, by virtue of the derivative, so I'll say derivative with respect to time here, I can find the velocity as a function of time, because by definition, the velocity as a function of time is the rate of change of position. What I need to do here is, knowing the velocity as a function of time, I would very much like to go in reverse and find the position as a function of time. That is not an option, because what my technique will get me, if I finally get around to stating it, what the technique of integration gets me is not the position as a function of time, but the change in position, delta x. It gets me displacement, which may or may not be a function of time. Usually, if I'm talking from a particular instant to a final instant, the displacement is not a function of time. It's a fact. So many meters of displacement. When I take a course in calculus, the reason why I'm stressing this is just partly for my own entertainment, but also, as I say, for the precision of the thing. The process of integration is sometimes referred to as the antiderivative. Oh, you just do the derivative backwards. I can understand why someone would say that, but I'm going from position as a function of time to velocity, and then I'm going from velocity not back to position again. It's not symmetric. It doesn't have that symmetry, and as a physicist, I'm always looking for symmetry, and this doesn't have it. I have position as a function of time, and the derivative gets me to velocity. When I apply this technique of integration, I go from velocity as a function of time to displacement. And I'm stressing it in particular because now what I'm going to do is to have a look at further down my equation sheet at the rule for the integration of a monomial. So we see notation has changed here. The integral of x to the n dx is equal to, oh, gobbledygook, gobbledygook. Look what's happening. I promote the exponent and then divide by the promoted exponent. Notice how the exponent here, which is x to the n, becomes n plus 1. I promote the exponent. And then I divide by the promoted exponent. It's like it's differentiation in reverse. I promote the exponent and then divide by the promoted exponent. It's very much like differentiation in reverse. Written here is a fancy math equation, but let me take my example again. I had said that if I had 3x squared, that taking the derivative was quite simple, because I'll bring the 2 down and I'll multiply, it becomes 6. Demote the exponent is 6x. That's differentiation. That's the power rule of differentiation. 2 comes down and multiplies, demote the exponent, bam, done. The integration works the same way. I will promote the exponent, so x to the first becomes a 2, and then divide by the promoted exponent. 6 divided by 2 is 3. It's differentiation in reverse. It's the antiderivative, except that it's not, because when these things have meaning, I have not achieved the position back again when I integrate, but in fact, the displacement. So I'm going to apply but Charlie, why is this the rule? Why? That's an issue of a course in calculus. You may find that very interesting, how that all works out theoretically, so that I end up with that equation. But I'm doing cowboy calculus here. I have a problem that I need to solve, and I'm simply going to use a pattern of calculus to solve it. So here I go, a very, very essential, well, there I go again, saying very essential. It's like saying very historic. It either is or it isn't. An essential application of calculus to our physics. Here I go. I have already suggested that I would like, that on many occasions I'll have the luxury of solving problems of motion with constant acceleration. And so I suggested if the acceleration is constant, what should the consequences of that be? And then I have a set of 3 equations that I derived algebraically. V is equal to V naught plus AT is just the definition of acceleration, so there's no work at all to get that. But with a little bit of algebra that we now understand very deeply, I have x is equal to x naught plus v0t plus 1/2 at squared, and v squared is equal to v naught squared plus 2a delta x. I can solve problems of kinematics. I achieved that by assuming that the acceleration was constant and impressing upon you that a fact of constant acceleration is that the velocity on average can be written as the initial velocity plus the final velocity divided by 2. And I leveraged that algebraically to come to the results. Now I'm going to proceed a different way. I'm going to do the following. I'm going to begin by saying let the acceleration be equal to some constant value. That says cost. Let the acceleration be equal to some constant value. Meant for that to say const. That is not always true. In fact, many of the wonderfully interesting problems that I will solve are problems in which the acceleration is not in fact constant. But let's presume for a moment that the acceleration is a constant. Well, the acceleration by definition is the derivative of the velocity with respect to time. I'm going to apply a bit of algebra to this and solve for the differential of velocity. It is kind of a big deal here for you to always be thinking about these differential quantities in terms of their true meaning. dv, the differential of velocity, is an infinitesimal change in velocity. An infinitesimal change. And I get an infinitesimal change in velocity by accelerating for a little bit of time. Now, in this case, the acceleration is constant. It's got no t in it. But if I accelerate for a little bit of time, I get a tiny, tiny little bit of change in velocity. Which, that's not good enough. I want the whole change. I want the whole change. Well, no problem. I will add up all the little changes. I can't stress this enough. This is not only how you do calculus, blah, but it's also a strategy for investigating physics. If you're a person who invents new physics, derives new laws and whatnot, if you want to discover the change in a quantity, you may first want to say, well, I can't tell you what the change is. First, let me investigate what would be an infinitesimal change when I change these variables an infinitesimal amount. What is the infinitesimal change? And then find the total change. So I write the infinitesimal change dv, and then I add up all of those infinitesimal changes. Of course, rules of algebra still apply. I'll also integrate the left-hand side of my equation. Oh, it's like the number one lesson of the day. When I add up all of the little dv's, I do not get v. When I add up all the infinitesimal changes in v, I do not get v. I get the change in v. I get delta v. So delta v is equal to the integral of the acceleration dt. But Scheidly, I don't know how to do integrals. Yes, you do. Because this is just a monomial change. It's a power of t. I'm not writing it here, but this is a times t to the 0 power. A times t to the 0 power. Anything to the 0 power is 1. So it's a times 1. It's just a. But with a little imagination, it's a times t to the 0 power. And according to my rule of integration, what I should do then is promote the exponent. So t to the 0 will become t to the 1. So a t will appear. And then I'll divide by the promoted exponent, which is dividing by 1, which does nothing at all. And so the result of this is a rather unimpressive acceleration multiplied by time. Every one of us starts to create shorthand in our mind of how these things work. Whenever I see a constant and I integrate, I'm just going to add the variable on there because it just appears. In my mind, I am not thinking this rule unless I'm doing some complicated situation. If I have a constant, then the t appears. So the integral of a dt is just a times t. So what I have from this equation is that delta v is equal to a times t, but appreciate the fact that delta v is the change in the velocity, and therefore the final velocity minus the initial velocity. That is, at is equal to the change in velocity, is the final velocity minus the initial velocity, and a little bit of algebraic jiggery-pokery, and v is equal to v naught plus at, which is one of my kinematic equations. Not defined on average, not derived on average, but instantaneously. You say, well, Scheidly, it's not much of a feat because I already derived it algebraically. I already know that this is true. Once we master this technique, of course, we'll be interested in what happens in the case where the acceleration is not, in fact, constant. For example, if the acceleration were linearly dependent on t, the acceleration just increases, increases, increases. Well, then I would get a different result for the velocity as a function of time. I would not get one of the famous kinematic equations. I would get a new equation. I've warned you before that it's a very popular thing on physics exams to show you a situation where you're really tempted to use one of your favorite dyed-in-the-wool kinematic equations. But you can't, because those equations are only valid when the acceleration is constant, as I'm deriving here. Now, consider, please, just like I did to start here, that the velocity is equal to the derivative of the position with respect to time. That's true by definition. I'll rearrange this in the same way. There's a lot of symmetry to what I'm doing, as there always should be. Stirring this around algebraically, solving for dx, an infinitesimal change in x, is equal to the velocity multiplied by time. That is not surprising. That is not surprising. If I go along with a particular velocity for, dt. If I go along with a particular velocity v for an infinitesimal time dt, my position will change by an infinitesimal amount. An infinitesimal change, delta x. I don't want the infinitesimal change, I want the whole change. And so I will integrate both sides of the equation, dropping an integral sign in there on both sides of the thing. When I integrate dx, when I add up all of the infinitesimal changes in x, I get the whole change, delta x. When I add up all the infinitesimal changes, I get the whole change, delta x. But I'll have to integrate the velocity dt. Well, what? I don't know anything about the velocity. Well, sure I do. I know that the velocity is a function of time is equal to the initial velocity plus the acceleration multiplied by time. I just did that. Now, I'm not including parenthesis on it. Maybe I'll include parenthesis, fine. I'm integrating that whole thing, v naught plus at, but it's not a bother because in quite a lovely natural way, the integral of a sum is the sum of the integrals. So I just integrate each part one at a time, and it's fine. This is v naught here, focusing on this. This is v naught multiplied by t to the 0. It's the same thing that happened up here with the a. A didn't have any t. V naught is the initial velocity. It also is not a function of time. The initial velocity is a fact. It is a constant value. It's not changing with respect to time. So it's v naught times t to the 0. Promote the exponent is t to the first. Divide by the promoted exponent is 1. It's v naught times t. Just as a became a times t, v naught becomes v naught times t, promoting the exponent. In a way, you like taking a derivative because it smashes down the exponents and makes the math easier. And you're scared of taking integrals because it promotes the exponents and makes the math more complicated. There's nothing you can do about that. It's just the nature of things. Now the second term, a times t, this is a bit more complicated because it's a times t to the first power. Well, I'll promote the exponent, so I'm expecting a t squared. But I also divide by the promoted exponent. Plus 1/2 a t squared. Well, would you look at that? The displacement delta x, which is the final position minus the initial position, is equal to the initial velocity plus times t plus 1/2 a t squared. Or in other words, x is equal to x naught plus the initial velocity times t plus 1/2 a t squared. No matter how many times I do this, I always enjoy it. There's a great satisfaction and surety in it. It's comfortable, it's familiar, it's a warm blanket. It's possible, though, that you're looking at this and saying, oh, Scheidly, come on, it's rather obvious. I knew it was going to work out that way. It's very, very simple. I would like to do more complicated problems. Well, in order to do a more complicated problem, you simply have to decide to make the acceleration some function of time instead of constant, and your physics becomes more interesting. It's my expectation, if we should come to a point where we have a test, that you might be confronted by one of those situations. Nevertheless, integral calculus is what makes it possible for us to calculate the total change from infinitesimal changes.